Chapter 12, Deflection of Beams and Shaft, Moment Area Theorem, Example 9, Solution 2, Consistency of Displacement. We have solved this problem in previous video with the use of a moment area method, which is a almost easy approach for solving such problems, rather integration. uh, rather using the integration method. But this time, the solution 2 is based off a very a far simpler approach, which is a consistency of displacement. Let's see how that goes. So again, in this problem, we have a two simple support beam handling a uniform load of W, and at the center of this symmetric beam is located an spring with the stiffness of K. Mhm. So again, in solution to consistency of displacement, we need to cut the section at before B and just develop the uh, moment equation to get the reactions like previous method. 5 over 12 WL is RA is equal to RB. Both supports are identical to each other and are both equal to 5 over 12 WL. So due to sigma Fy equal to 0, like the previous example, it should cancel out. Again, this is not 0, that's a 2WL that should cancel out, but the vertical load apply at the top, so that's 2WL, and that simply gives us Fs is equal to 7 over 6 times WL. F of force of a spring is a 7 over 6 WL. And so far, the solution of consistency method until you get reactions and for both supports and also for spring was is identical to previous method, but the difference is starting from here. So if we look at the configuration of the beam, we can easily see delta B is equal to Fs time over Ks, force of a spring uh, over the stiffness of a spring. At the same time, we do know due to uh, if you look at this point, you can easily see a spring and beam are connected to each other, so they should move with each other, either upward or downward. So there is no other way but moving at the same distance. So that's how consistency of displacement comes to play and made the problem even far simpler than moment area method. So how that goes, one can say now I can just by applying a superposition rule, I can uh, di- divide my structure to two parts. Like a when you have only a simple support, two simple support beam with uniformly distributed weight of W without this spring, and the other time is the just the beam, but this time the first time is just the beam uh, with the loading without the spring, and the other one is the beam without loading but the spring for effect of a spring, which is a upward pull, upward push from the bottom of the section. So after calculation of force of a spring, which we already did, and that's 7 over 6 times WL. Uh-huh. One can easily say, do you remember we were discussed about the displacement of a two simple support beam with uniformly distributed load of W, and that was 5W times L to the power of 4 over 384 EI. but our length is just here, it's 2L. Just be careful about that. So that's the displacement for the first structure, first part, and with superposition method plus the other one is just if you remember, if we just have a two simple support beam with a concentrated load at the center, we also calculate this one. I can provide you with both of those videos if you want to review them, and that's a plus a force. Uh, just consider that's a concentrated load. Forget about force of a spring. Just a concentrated downward push, and that's P L cubed over 48 EI. Do you remember? That's a let's draw it very quickly. So if we have a two simple support beam with the length of L and P. So if you remember, we talked about that delta maximum happens at the center, and that delta max is equal to PL cubed over 48 EI. Mhm. Again, I will provide you with that link to see how you can calculate the effect of a two simple support beam handling a concentrated load at the center. So the only difference here is our push is upward. So that's our deformation. That's our delta max. Mhm. And that's a the length is just 2L. The length of the beam is just goes by 2L. So that's P 2L cubed over 48 EI. And due to consistency of displacement, the overall displacement of the configuration is also equal to a delta S is equal to delta B. They have no other way to but to move at the same amount. So delta B it just comes from the effect of loading on beam, and Fs over Ks is the based on action and reactions. One of the forces applied to the beam, and the other effect is applied the same amount, just different direction, opposite direction goes for a spring. So that's Fs force of a spring over stiffness of a spring. So let's make it a bit clean. If you do so and solve it for the only unknown of the problem, because we already know what Fs is, the only unknown is the stiffness of a spring. So if we rearrange our equation and jot it down based off Ks, stiffness of a spring, and just you cancel out the term you can cancel with each other, and at the very eventually you will be having this equation 2ks times L cubed is equal to 28 times 6 EI. If you cancel it out a bit, if you rearrange it a bit more, it just gives you a Ks stiffness of a spring is 84 EI over L cubed. Ks stiffness of a spring is 84 EI over L cubed. Hmm? And that's what we solved in previous example by calculating the moment area, second moment area theorem area under the m over ei times the centroid to one of the uh, points. So this is far simpler, and yet if you complete the problem, it just says if you have delta, and in that case delta b, as soon as you have delta or ks, because fs is unknown, you can easily calculate both of them. So thank you. This is the second approach for a previous question, which you can easily see how it made it far simpler. Thank you.